So today I'm going to talk about in-situ electron microscopy characterization and also development of energy storage materials, and talk my work on how do I combine in-situ electron microscope and material characterization with material development to make a new energy storage materials. So starting from my background, but since this is my second presentation, I'm just gonna go over very briefly. So at the early stage of my career, I did work on the atomistic simulation and try to understand what is fundamental physics in the materials, right? And doing the density functional theory and molecular dynamics calculation. And also develop some of the accelerated molecular dynamics techniques to calculate gas transition and also oxygen transport in the solid oxide fuel cells. Then later in 2010, I joined a postdoc in UPenn and worked at Sandia National Lab. At this time, I started working on in-situ transmission electron microscopy and trying to study the electrochemistry in the lithium-ion batteries. So basically making a really tiny battery inside the electron TEM and observe the reaction in the atomic scale. Okay, then in 2017, I joined UCF at the current position at assistant professor at material science engineering. And my research area is in-situ TEM and energy storage materials. And also I work on the nanomechanics and applying the stress strain in the inside the microscope and see how the materials deform in the atomic scale. Okay. So if you're interested, here's my group webpage, and please contact me if you have any further questions. Here's my email address. And here are some of my teaching experiences in UCF. Basically, I teach electron microscopy courses and some of the material science engineering courses. Okay, so let's go into my research. So I'm developing energy storage materials, and lithium-ion battery is a key key battery technology that's going around, very commonly used in all kinds of applications, starting from portable electronics all the way up to electric vehicles. But there are different requirements for different applications. But the most important thing will be listed here: the cost, because you want to have the lowest price for the batteries, and also the safety, so you don't want to have any fire-related accidents. And you want to have large energy density because you want to make the battery compact and light. So you can you can use it for various applications. And especially for the electric vehicle, you want power. So you want to have very fast charge and discharge capabilities. And of course, you want to have a long cycle lifetime. Because for the electric vehicle, you want the battery to last at least the life of the car. So more than 10 years need to be guaranteed with these batteries. And because these batteries are used in different temperatures, you want to think about temperature stability and work on different temperature regions. So here, the current lithium battery technology is still not enough for some of these technologies. So recently people are trying to develop more advanced lithium batteries using high voltage cathode or high energy density anode. So here, basic structure of lithium battery chemistry is still the same, but you want to use advanced materials to enhance the energy density and also the cycle lifetime. And there are also lots of different chemistry that is proposed. One of them is a lithium sulfur battery, which uses sulfur as a cathode, which has a very large capacity, but with some decrease in the power densities. But so here, let's just move on. So in my research, I've been developing different lithium-ion battery anode and cathode materials. And here is one example of these materials. So lithium-ion battery is already a high energy batteries, but you want to extend it with a more higher capacity anode. And one of them is lithium metal. So if you can use lithium metal as anode, you can jump the anode capacity by 10 times the current graphite. But the key here is this lithium causes lots of issues, like it can cause dendrite, very sharp lithium pillar that can extend down to the other cathode, the other side into the cathode, and the short circuit, and that can cause fires. And also there are lots of reaction going on, and so you want to prevent all these unwanted reactions with the lithium. So here I've been developing the coating technologies on the anode side to prevent this lithium metal dendrite, so you can extend the cycle lifetime. Okay, so here the idea here is to use a liquid metal as a coating material on the anode to prevent the lithium dendrite. So lithium metal, this is a is a liquid at the room temperature. So this is a gallium-based alloy. The melting temperature is about minus 10 degrees Celsius, so you can maintain the liquid state in operating temperature. So what you do here is you coat the liquid metal on this copper current collector. So what you see is you have bare copper, which is rough on the surface, but by applying the liquid metal on the surface, you can create very smooth surface that you can promote the uniform deposition of lithium. And this liquid metal is based on gallium, which reacts with lithium. So it attracts lots of lithium. So the wetting performance of, for this liquid metal is good against the lithium. So if you do this, if you try to deposit lithium, you can decrease the over potential. So you can here, so with and without liquid metal coating, you can significantly lower the over potential, reaction over potential from the blue line to the red line. So you can easily spread the lithium on this coating. And because of this, the liquid nature of this coating, even if you put the lithium on, once you take the lithium out, then this liquid coating transits from solid to liquid and back and forth. So you can make it's some kind of like self-heating coating that will enhance the lithium materials. And by using this coating, you can significantly enhance the cycle lifetime of the lithium. So this is combined the full cell with significantly large capacity, right? So you can see from non-coated copper to the liquid metal coated copper with a different electrolyte, you can significantly enhance the cycle lifetime. Okay, so that's for the materials development side. And I'm also working on the in-situ TM on the electron microscopy. So here, using a lithium metal is a key for the advancing the lithium ion technology. But if you want higher capacity and density, power density, it causes another issue. Like because you have so much energy stored in the batteries, if there's some flow or some accident, it can cause a significantly fire accident like this. And if you want to extend it to the further by using the lithium metal batteries, you will create these dendrite issues. So the new technology has been run to use all solid state system that uses solid electrolyte instead of liquid, so that can prevent the lithium dendrite from going through the electrolyte and reaching the other side of the electrolyte. But still, this solid electrolyte causes issue because there can be a lithium dendrite penetrates through these grain boundaries and reaches the other side, just like this, showing this images here. So you want to understand this complex electro-chemo-mechanics in nanoscale, and I've been working on developing this in-situ TM technique to directly observe the dendrite growth procedure and measure the stress or the force that is being applied to the electrolyte. So here we have this setup with an in-situ TEM holder. You mount an AFM cantilever, which is conductive, and you can apply current to grow the lithium dendrite here. So here's one example of the movies. So if you apply the bias, you can see the dendrite starts growing at this cantilever, and as it grows, it's going to push this cantilever away from this electrolyte. So by measuring the displacement, you can quantify how much force that has been applied to this dendrite and also to the cantilever. And you can see, based according to this applied force, the growth direction will change from the vertical growth to the horizontal growth once it reaches the threshold. And you can also combine it with a theoretical calculation. And we found that by applying the compressive stress, that at the lithium surface, it becomes more easy to form the vacancy compared to the atoms. So if there's a stress, there's a driving force to move the lithium away from the compressed area to the lower stress region. And we've been doing this experiment for different conditions. And if you apply higher voltage and have a higher growth rate, there will be a larger force that's going to be applied to this dendrite and also the electrolyte. Okay, so that's for the in-situ microscope. And I've been also working on the cathode side. So I've just introduced anode and electrolyte, now going to the cathode. So for the cathode side, I've been working on lithium sulfur batteries, trying to develop new composite to enhance the cycle lifetime and also the power densities. So here, what we used is this VAT die. So this is the graphene-like structure with some of the functional groups like oxide or hydroxide groups. Okay, so we use this and modify the carbon cloth. Then later you infiltrate lithium polysulfide into it, and they will create a nanopolar structures that confines the lithium polysulfide. So you can see from this TM image, the sulfur is uniformly distributed in this pores, which is about 5 nanometer in size. And you can use this to the in-situ microscope and directly observe how this reaction takes place in this kind of environment. And reaction takes place really quickly across these materials. And you can see there is not much volume change, which is good for enhancing the cycle lifetime. And you can also measure the reaction rate. And you will see that the reaction can take place really quickly if the size scale is within a couple hundred nanometers. But this is a diffusion limited process. So if you increase the size, go up to like micron scales or like 10 microns, then the reaction will take like hours, like about 10 hours if you extend this to the micron scale. So having the nanoscale microstructure is very important in this kind of structure, and it confirm the performance of these materials, and it has very good improved capacity and also the cycle lifetime compared to the one without this modification. Okay, thanks for getting my time. So finally, I just want to acknowledge my students and collaborators, and also the funding sponsors for this research.